Welcome to This Explainer. Today, we're diving into what is arguably the ultimate technological paradox of our time. We're talking about quantum computing. Now, on one hand, this is a technology with the mind-bending potential to literally save our planet, cure complex diseases, and generate over $1 trillion in value. On the other hand, it possesses the sheer computational power to completely break the internet and unravel our global digital security. It's a high-stakes race, for sure, and we're going to break it all down using the latest research. Okay, let's dive into this. Here's our roadmap for today. 1. The quantum paradox. 2. Simulating nature's secrets. 3. The hardware reality. 4. The cybersecurity nightmare. And 5. A matter of ethics. Section 1. The quantum paradox. Let's look at why we absolutely need a total paradigm shift from classical computing in the first place. To really get this, we have to look back at a quote from 1981 by Richard Feynman, one of the founding fathers of quantum computing. He famously said, "Nature isn't classical. Damn it, and if you want to make a simulation of nature, you'd better make it quantum mechanical." Basically, he hit the nail on the head. The physical world, molecules, proteins, chemical reactions, it just doesn't operate on simple binary logic. So to actually simulate complex natural processes, we need a machine that plays by nature's rules. And the reason why becomes super clear when we compare the two. Classical computing, like the phone or computer you're using right now, runs on binary, sequential decisions. It's just a series of yes or no, 1 or 0 switches. Quantum computing, though, it utilizes distributed probability amplitudes. Thanks to wild physics concepts like superposition and entanglement, quantum bits, or qubits, can exist in multiple states at exactly the same time. This means instead of trying one solution after another one by one, a quantum computer can explore massively complex high-dimensional problems exponentially faster. It's a complete game changer. Section 2, Simulating Nature's Secrets. So, now that we know how it works, let's explore the mind-bending potential this has to heal our planet and even ourselves. According to data from BCG and McKinsey, the real-world applications here are staggering. Take fertilizer, for example. The century-old Haber-Bosch process we use to make ammonia eats up to 5% of all natural gas globally. But quantum computers could help us accurately model complex molecular interactions to create new catalysts for green ammonia, drastically slashing those emissions. We're also talking breakthroughs in green hydrogen, way better carbon capture, and new polymer concretes that are actually lighter and stronger than traditional cement. And in life sciences, well, by enabling ultra-precise predictive modeling without needing endless wet lab experiments, quantum tech could totally revolutionize drug discovery. It could target incredibly tricky diseases like Alzheimer's, potentially creating up to $500 billion in value for the pharma industry alone by 2035. And if we zoom out and look across all industries combined, McKinsey projects that quantum advancements could generate a jaw-dropping $1.3 trillion in value by 2035. That is the sheer economic gravity of this technology. But before we get completely carried away, Section 3, the hardware reality. Because actually building these machines is arguably one of the greatest engineering feats in human history. Now, what's really interesting about this hardware setup from Intel Labs is that it literally looks like an intricate golden chandelier. The sheer complexity required just to make a quantum chip function is wild. All this massive, highly specialized equipment is needed because qubits are unbelievably fragile. I mean, the slightest interference, even an unintended observation or a tiny ping of radio frequency noise, can completely wipe out the data. Right now, we're in what researchers call the NISQ era, which stands for Noisy Intermediate Scale Quantum. Basically, we're dealing with systems that are still pretty prone to errors. And to keep that noise to an absolute minimum, these systems need extreme conditions. This Intel researcher is operating a testing system that has to be kept at roughly 20 millikelvin. To put that into perspective for you, that is an incredible 250 times colder than deep space. Because of these massive hurdles with scaling and error correction, Intel estimates the industry is still a good 10 to 15 years away from large-scale commercial viability. However, that 10 to 15-year timeline brings us to the real plot twist of our explainer. Section 4, the cybersecurity nightmare. I want you to really think about this chilling question. What if hackers are already stealing your encrypted data right now? According to a systematic review from the NHJS, our current global digital security leans heavily on encryption schemes like RSA and ECC. Sure, those are mathematically secure against normal classical computers, but the sheer computational muscle of a mature quantum system will be able to rapidly decrypt them, completely dismantling the protocols that protect everything from your bank account to national security. Which brings us to a terrifying strategy called HNDL, or Harvest Now, Decrypt Later. Here's the thing. Adversaries don't actually need a quantum computer today to do damage tomorrow. They are simply intercepting and hoarding highly sensitive, encrypted data right now. When quantum tech finally matures, they'll just unlock the whole vault. And the research highlights this isn't just a theoretical threat. Massive swaths of internet traffic have already been caught being suspiciously rerouted and intercepted by state-level adversaries, entirely anticipating this exact technological leap. So what's the actual timeline for this threat? Based on a 2024 survey by the Global Risk Institute estimating the likelihood of a quantum computer being able to break standard RSA 2048 encryption within 24 hours, the window is definitely shrinking. Within a 20-year timeframe, experts assess a 31% probability of an RSA breach. That is nearly a 1 in 3 chance that our current encryption standards will be entirely compromised within 2 decades. Which brings us to a concept known as the Mosca inequality. You can think of this equation like a ticking time bomb in a thriller. It basically states that if the shelf life of your sensitive data, plus the time it takes your organization to migrate to a new quantum-safe system is greater than the time it'll take for a quantum computer to be viable, well, you're already at risk today. Think about it. If your data needs to stay secret for 25 years, and it takes 10 years to upgrade your systems, but a quantum computer arrives in 20 years, your data is exposed. And this brilliantly illustrates how even our most modern security frameworks have weak spots. People often point to blockchain as the ultimate secure, decentralized system, right? But according to the NHSJS review, the cryptography used in most current blockchain protocols like Bitcoin and Ethereum is actually highly vulnerable to quantum attacks. Moving to post-quantum cryptography, utilizing resilient algorithms like Kyber or Falcon, provides high quantum resistance for sure, but it comes with immense adoption complexity and requires completely overhauling existing infrastructure. With such a massive transition required, we have to look at the broader societal picture. Section 5, a matter of ethics. How on earth do we tame this double-edged sword without leaving half the world behind? When you look at global investment in quantum computing as a percentage of current GDP, it reveals a remarkably stark disparity. The deep blue areas are heavily investing, while the lighter areas are severely lagging. The research points out that over 60% of developing countries lack the basic infrastructure even needed for this digital transformation. Because quantum systems are so complex and expensive, they're being hoarded by affluent nations and huge corporations. This risks an unprecedented global digital divide, where under-resourced regions become sitting ducks for cybersecurity exploitation and get completely shut out of a trillion-dollar quantum economy. To prevent that scenario, the sources outline some very urgent, actionable steps. First up, organizations and governments globally have to start an immediate transition to NIST-certified post-quantum cryptography to lock down sensitive data. Second, to decentralize the research pipeline, we need serious funding for localized labs, educational scholarships, and public-private partnerships in emerging economies. And finally, forming a UN Quantum Ethics Consortium. A global treaty, kind of modeled after the GDPR, could set international standards for data sovereignty, cryptographic resilience, and ensure developing nations are actively brought into the fold with technical training and aid. So what does this all mean? We are literally standing at the threshold of a computational revolution that will redefine reality as we know it. The science is moving incredibly fast, and the stakes, from curing Alzheimer's to protecting the entire global financial system, could not be higher. So I'll leave you with this. Will humanity safely tame the quantum beast through proactive collaboration, or will we let a lack of preparation break the internet? Thank you so much for exploring this fascinating explainer with me, and definitely keep your eyes on the quantum horizon.